So we're now going to look at the problem of solving ax equals b a little bit differently. We're instead going to look at it as starting with a matrix A and computing what's called an LU factorization of it. So if you start with matrix A, then under some mild conditions, which we'll discuss next week, there exists a lower triangular matrix L, actually not just a lower triangular matrix L, a unit lower triangular matrix L, and an upper triangular matrix U, so that A can actually be written as the product of matrix L with matrix U. Why this is significant will become clear towards the end of this discussion. Okay, this is known as an LU factorization of a given matrix A. So given matrix A, the purpose of the game is to compute matrices L and U. Now, we're going to just push symbols. So all of your training up to this point, all of these weeks of working with slicing and dicing matrices and trying to understand matrices in terms of different parts of the matrix, actually was meant to lead up in part to this right here. Quite often people won't see this until a graduate course. So don't be scared. I have faith in you. You're going to be okay. And actually, whether you're okay or not is not that important, because as long as you understood the first part of this week and did well in it, you'll be just fine, because that's the part of this material that you would have been taught in an ordinary linear algebra class. So we're just going to be going just a little bit beyond. I think you'll be good. We start with matrix A, and notice that we're partitioning, we're slicing and dicing. And what we do is we partition so that we identify the top left entry in it. And notice that therefore below it is a column, which is then a column vector, and the rest of the row, which is a row vector, and then the rest of the matrix, which we'll call A22. Now similarly, we partition matrices L and U. Now notice that because L is unit lower triangular, it's guaranteed that this entry right here is a 1 if you split off just one scalar there. Notice that because L is unit lower triangular, L22 is itself also unit lower triangular. And then we take upper triangular matrix U and we partition off its first entry, which of course means that there are zeros then below that. And then also notice that U22 therefore is itself an upper triangular matrix. If you just think about it for a second, you'll come to that conclusion. We want to compute L and U such that L times U is equal to A. So we just write down that equality, and that's going to drive a lot of our discussion. All I'm doing here is I'm taking my partitioned matrix A and I'm plugging it in for A in this equality. I'm taking my partitioned L, plugging it in for L, my partitioned U, plugging it in for U. And what we get then is this right here. So we do slicing and dicing, and now we do some substitution. All very good so far. Purpose of the game is to figure out what these different parts of L are and these different parts of U are. Okay? And notice that we need to come up with formulas for those different parts in terms of the elements of A, because we know what the elements of A are. So we need to do some kind of computation with the elements of A in order to compute the different parts of L and U. How do we do that? We can multiply all of this out. Actually, I should have gone like that. And what we get when we do that is this times that plus this times that for this top left entry. Right here we get this times that plus this times that, or that. This times that plus this times that, or that. And finally this times that plus this times that. And then we can say, oh, but here this is just 0, this is just 0, this is just a 1, get rid of a bunch of stuff. And then the idea is that we know that this matrix is equal to this matrix only if it's equal to this matrix. And therefore the different parts of these two matrices, for example this, must be equal to that, this must be equal to that, and so forth. And if we set those equal, what we get is this right here. So this now directly ties values in U and L to values in A. I'm just repeating here what you just saw a second ago. And what do we know? Well, let's have a look here. We know what alpha 11 is. Therefore, we know what epsilon 11 is. In other words, we can determine what this first entry of U is. Like that. Similarly, we know what A12 transpose is because A is given, and therefore we can determine what U12 transpose is, this rest of the row right here. It's just equal to A12 transpose. So we know that. So to compute U12 transpose, all we need to do is set it to A12 transpose. Now things get a little trickier. By the time we get here, we know what epsilon 11 is because we know it's equal to alpha 11. We know what A21 is, and therefore we know that L21 can just be computed as A21 divided by epsilon 11, which of course is just alpha 11. Now, by the time we now look at this right here, we know what L21 is, we know what U12 is, U12 transpose, we know what A22 is, so we can bring everything we know to one side, and what we then recognize is that what's left is to compute L22 and U22, but L22 is a unit lower triangular matrix, U22 is a upper triangular matrix, so all it says is once you update A22 by subtracting off L21 U12 transpose, what you want to do is proceed and find the LU factorization of that smaller matrix. And notice that this is a very special operation. It's a matrix from which you subtract a column vector times a row vector. A column vector times a row vector is an outer product. When you update a matrix with a multiple of an outer product, we call that a rank 1 update. So now we may have stumbled upon an algorithm. Okay. The algorithm is set epsilon 11 to alpha 11, set U12 transpose to A212 transpose, and as a matter of fact, we may just want to overwrite A, in which case we don't have to do any computation there at all. Then you can compute L21 by taking A21 and dividing it by epsilon 11, which of course is the same as A21 divided by alpha 11. And if we want to overwrite A with the result, then what we would want to do is set A21 equal to that. So notice that all we're doing is we're scaling by the inverse of alpha 11. And then what we want to do is update A22 by doing this rank 1 update. And then we want to proceed and compute the LU factorization of that updated matrix A22. We can summarize that all in the algorithm on the left. Okay, and let's illustrate what's going on the right. These were the updates that had to happen. Notice that we're updating A itself, so we're overwriting it. So therefore, for this, we don't need to do anything whatsoever. The current row, one could say, this is the current row. The current row is left alone. This part of A needs to be updated by dividing it by alpha 11. Okay, and that's because epsilon 11 is equal to alpha 11, and L21 is supposed to override A21. So we get this right here. And then what we need to do is we need to update A22 by subtracting off the outer product of L21 and U12 transpose, but L21 has overwritten A21, and U12 transpose is just A12 transpose. We saw that up here. So if we now illustrate what happens to the matrix along the way, we partition, we update, we move on. So this is the continue with this smaller submatrix, which means you partition, you update, and you move on. So what we have here is a new algorithm, which I guess I accidentally labeled Gaussian elimination. But if you think about it, this is exactly the algorithm for Gaussian elimination that we came up with before when we thought about it as applying Gauss transforms. So what we conclude is that LU factorization and Gaussian elimination with the matrix, reducing the matrix to an upper triangular matrix, is exactly one and the same thing. And notice that even the storing of the multipliers below the diagonal when the entries are being set to 0 is exactly the way it was when we did Gaussian elimination. So where is this going? Well, we want to solve AX equals B. We now know how to compute lower triangular and upper triangular matrices L and U so that A is equal to L times U. What we can do is take L times U and substitute it in for A in our AX equals B. We can then recognize that X can be thought of as a matrix and matrix-matrix multiplication is associative, so we can write it like that. And we can then say, well, we don't know X and therefore we don't know U times X, but we can give it a name. We'll call it Y, the vector Y. And what we know about Y then is that L times Y must be equal to B. But solving Ly equals B for Y is a lot simpler. That's solving a lower triangular matrix, and we already saw that solving an upper triangular matrix was backward substitution, and that was straightforward. This is just the equivalent with a lower triangular matrix. Then we can take that vector Y once we've computed it and say, oh, but U times X has to be equal to Y. So now we can solve for vector X. And notice that that's solving with an upper triangular system, but solving with an upper triangular system is easy as well. So we first factor A into L times U, and then to solve the linear system, all we have to do is solve with a lower triangular matrix and solve with an upper triangular matrix. So in summary, under mild conditions, we can take A and factor it into L times U. The factors L and U can actually override the matrix A. Well, actually not quite, because notice that there are these entries of L that are equal to 1 on the diagonal, and they would also have to be stored in the same place where the corresponding entries of U, the diagonal entries of U, would have to be stored. But we know that those entries in L are 1, so therefore we don't need to store them. And we noticed that the algorithms that came out were absolutely identical, so LU factorization is simply Gaussian elimination.